Great.
Let's go.
Okay, great. Yes, so when we saw the program and we saw that there was Martin and me separately, we just couldn't do it. And so we'll do all the 4 hours somehow together. And we were actually thinking quite a long time about how we do this. Because we feel that while many of you are oceanographers by training to some degree, we are not sure how many of you have actually ever had any formal introduction to physics of sea ice. Who could derive Stefan's law? Good.
What's your name?
But that's really that's what we were expecting. And so what we'll do is we will combine like 4 different lectures into 4 hours. So what we'll do is we really start from scratch how sea ice works, really basic introduction, and we'll then move on to Southern Ocean sea ice interaction, etc. And so it'll be a bit of a steep learning curve. But we try to really stick to the essentials and make it fun. As always, if anything ever should be unclear, please interrupt anytime. We both love to be interrupted because it shows us that you're still with us. Great. And we thought we hijack David's idea and briefly introduce ourselves in terms of how we ended up standing here. And so for me, many years ago, I started studying meteorology in Hamburg. So I'm a meteorologist by training. And then during my studies, I figured out that I really like the polar regions. I've always been fascinated by North Pole, South Pole, explorers, stuff like that. And then I realized there is a small university in Svalbard. So Svalbard main city has 2,000 people living there, and these 2,000 people decided it's a good idea to have a university. And so I went there for 1 year during my studies. All my professors hated it. They all said, you really shouldn't go there. In your CV, it won't look good. People think you'll just have had fun up there. And I never felt like having fun is a bad thing in life. And so they wanted me to go to whatever, New York, London, whatever big name university. But I said, no, I'll go. And so I went up here for 1 year. And I fell totally in love with the Arctic or ice in general. And while I was up there, I met a professor from the University of Washington in Seattle. And so what happened the next is that for my master's thesis, I went to the University of Washington, working on how sea ice bottoms evolve in summer when there's freshwater layers and they might refreeze and stuff like that. So I went to a university with a better name than University in Spitsbergen. And while I was here, I met another professor from the University of Cambridge in the UK. And so he asked me whether I would like to do my PhD with him, and I said, yeah, why not? And so for my PhD, I went to Cambridge. So I spent a bit over 3 years there, working on salinity of sea ice, interior of sea ice. And then from there, I took on a postdoc position in Hamburg at the Max Planck Institute for Meteorology. Then that developed into a group leader position. And then, some 3-4 years ago, I moved to the other side of the building where the university was located in Hamburg. So since 4 years, I'm now at the University of Hamburg. Long story short, 2 lessons to be taken away. Go wherever your heart takes you. Don't listen to people who think, oh, that won't look good. And second lesson, to be honest, I never had any plan. And so I just took up the opportunities that arise out of nowhere. And that brought me here. I'm not sure if I would be here if I had this plan from the beginning. And so if you pursue a career in science, being happy by not having a plan, I think, is a really good character trait. So that's me.
Hello. Me, I had a plan. My plan was to do, I spare you the first 18 years of my life. Let's not mention that right now. But my plan was to do particle physics. I wanted to understand the world. And so I went to the University of Louvain. I will show you, I have the same problem. I went to the University of Louvain in Belgium. which is my home country, in this beautiful tower, and try to study particle physics. But after 6 months, I figured, okay, finally, I don't really like making 30 pages of cross-section calculations to get a number that I don't even understand. And so I was a bit desperate, and I bumped a door. And so the particle physics department was there, and that level was the kind of nasty climate scientists who are not doing correct physics department. But I was desperate, and so I climbed the stairs and bumped a door and asked whether I could do anything. And the guy was doing sea ice. So this is how I came into the field of sea ice, completely randomly. I did my PhD there. I developed a sea ice model, which took me to Paris, which I kind of hated. I didn't really like the place. There were too many people. My first girlfriend dumped me there as well. So it was not really cool, but I decided to go to the United States, same place as Dirk, but years later. I did a postdoc, and finally I ended up in Paris anyway, because there was some space for me apparently there. So I'm still there. It's been 11 years. And meanwhile, I also met Dirk many times because our PhD topics were quite related. And at some point he said, oh, you should come and teach with me in Svalbard. And since 2015, we are sharing a course there with Frank Nielsen. And so my take-home message is that probably I have something to do with 1960s towers, because if you look at the different buildings, they share some similarity, but it's all random. That's the point. I didn't have a plan either, or my plan was wrong. It's full of contradiction and randomness, but in the end, it's really nice. Do you
still hate Paris?
No. I finally understood the place, and that's also a take-home message. It takes a bit of time to understand a place, and now I'm really happy. I think it's one of the best labs I can know. Very, very, very nice colleagues. Oh, and this is a little clin d'œil. I lead shaking to David. I never stopped playing music, so I took your message. I had a passion from. So this is me, you can't see, but it's me playing music at a concert somewhere in the neighborhood of Lille. Okay, so I'm supposed to do the first part. And so now we'll go to the serious sea ice business. The first thing I will do is try to explain you how, as oceanographers, you could view sea ice. And the summary message here is that sea ice is a small layer, but a small layer that changes the ocean. Let's have a look at how sea ice looks like. It can look like this. This is Antarctic sea ice. In spring, more than a decade ago already, I took this picture. I was younger. And sea ice is defined as any form of ice found at sea which originates from the freezing of seawater. It occupies a large surface of the ocean. It is also highly seasonal. Let's look at the Antarctic sea ice. Now you have the Antarctic continent, and then you have this area that is influenced or occupied some months of the season per sea ice. And what is shown is, here is the number of months when you have sufficient sea ice coverage. So blue means no ice, never. And red means ice all the time. And so from this you can see that there is a huge seasonal cycle between the summer minimum and the summer maximum. So you can notice that sea ice is beautiful, it is highly seasonal, but it's actually fairly thin. So if you look at the surface, you may see that this is, let's say, 1 meter, 2 meters thick. But if you look at the perspective from the ocean, this appears to be very thin. Let's look at how things look like if you take, let's say, a mixed layer. Sea ice would look like that. So it's not very big. But if you start to think about a deeper ocean, then you end up with a view like this, where this would be 300 meters of subsurface plus mixed layer, and a little bit of sea ice on top of it, which means it's really, really, really thin. So if you think in terms of storage problem, probably sea ice doesn't mean much. If you think at flux problems, then maybe you start to see things. But still, it is thin, but it changes how the ocean looks like. The first thing I think you can take from this is that the surface energy budget is going to be modified by the presence of sea ice. And I will give you the textbook view of what we think is the impact of sea ice on the surface energy budget. In terms of energy, I think the first thing I can tell is that the presence of sea ice is a sort of thermal buffer that prevents large departure from freezing temperature. There could be many ways to show that, but what I did is to pick up a plot from a paper by Violet and Pellicero. I looked at mixed layer properties under sea ice, and it's a temperature map in winter. And you see the black line here is the sea ice edge during this season, and you see that it's all blue inside this edge, which means that the mixed layer temperature is very close to freezing temperature. Looks evident, but that's because of two things. Sea ice forms when temperature is at the freezing point, and if you happen to bring in any heat, any sensible heat, it will be super efficiently transferred to sea ice and absorbed because the latent heat of sea ice is huge. So yeah, in practice, you have a temperature that's really stable. The departure is on average 0.1 degrees maximum from the freezing point. So sea ice makes a thermal buffer. The second thing is that sea ice is a screen. It is white. So I have two pictures from above. Sea ice from above, you have the sun, you see like, it's bright, it's reflecting the light. The reflection power is called albedo, and it's, let's say, between 0.5 and 0.7. So most of the light is reflected, and the remainder of the light that is going through the surface is actually very efficiently absorbed inside the sea ice. And so when you look from below and don't use Photoshop to modify your pictures, this is how sea ice looks like from below. So very dark. Okay. So means that the presence of sea ice drastically modifies the radiation budget. I have very simple scheme here between an ice covered surface and an ice free surface. 100% of light become 1% of light maximum in the ocean. It can be even less than that. As compared with the ocean, where about 90% is absorbed and a large part of that make it to the ocean. So once you remove the sea ice layer, you really start changing the surface energy budget. There is another important thing regarding energy, is that sea ice is like a lid that is also insulating. So as oceanographers, you may know that the surface energy budget of ice-free waters is dominated by sensible and even more latent heat fluxes, which can amount like, that's an order of magnitude, but hundreds of watts per square meter. When you put a sea ice layer in there, you prevent this exchange to occur, and you replace them by conductive heat flux through the ice. You will hear about that in a minute. And the numbers are even possibly high here. But tens of watts per square meter is what you're left with. Okay, so the two things combine, solar radiation screen effect and thermal insulation effects make that energy exchange are basically shut down when you have sea ice on top of an ocean. So you can take home message that sea ice drastically modifies the surface energy budget. we can discuss about ways to prove it, because I didn't really show data or numbers, but with experience, this story is really, really true, to the best of I can tell. The second things I'd like to raise is that the presence of sea ice is fluxing salt and fresh water, or taking up salt and fresh water from the surface ocean. And that's really a strong modification of the surface exchange of mass when sea ice is present. When you form sea ice, you will see this later as well, most of the salt is rejected to the ocean. The water goes into the sea ice, but the salt remains, so that you salinify the surface ocean. And in the polar regions, density is dominated by salinity variation, so that this salt rejection is a really efficient means to densify water. And that's what's illustrated in here. You have a beautiful or not, I don't know, scheme illustrating that when you freeze, you reject salt. And if you take Violen's paper and look at sea surface salinity under sea ice during the freezing season, maximum extent, then you see that in the regions where you grow ice, you have really saline wet waters. And this is because of the salt rejection effect. You actually form a lot of ice here and salinify waters. But when you melt the ice, you are only left with practically fresh ice, or ice with very little salinity. So when you melt ice, you reject or you release fresh water, and you freshen the surface. And you see this is what happens here at the ice edge, where ice is transported. And you see that the salinities are much less there. This is because of the effect of melting ice. And so effectively, sea ice is actually transporting fresh water from growth to melt sites, and that has a tremendous effect on the ocean circulation. It has been shown that you have probably several tens of spare drops that are generated by this process. You can look at density, things in density space as well. This is a cross-section from a South Pole to North Pole in the global ocean of neutral density, and you see actually that sea ice growth region acts to source dense water to the ocean. Yes, I think that's what I wanted to say about ice-ocean exchange of salt and fresh water, and I think they affect the ocean in many ways, and I just touched upon a few things, but we discover more and more how important that is. And the third aspect is the ecology, and you will hear about that, bless you. You will hear about that this afternoon. I think I just put together a slide to just illustrate how specific sea ice an environment is. I think it's the second largest biome on Earth after deserts, probably. So it's really a large ecological biome, and it's made of many small habitats. You have the brine habitat, but you also have pressure ridges. You have under ice habitats. It's super diverse, and it's host to many ecosystems. Within the ice, you have ice algae, but on top of the ice, you have birds and mammals that use these different habitats. So that's also completely changing the ocean. Probably I give the floor to my dear friend Dirk, who is going now to present you the rest of this talk.
Yeah, so what I thought I'd do first, to give you an idea as to, based on what Martin has just told us, we try to really teach sea ice from an oceanographer's perspective. Otherwise, we wouldn't be able to do it in 4 hours. So what we plan to do today is to really go through some of the fundamentals of sea ice growth, ice-ocean interaction, how does actually the ice bottom work, etc. and ice movement. And we'll probably move a bit of this part also into the second hour and then some of this over here. But that's the general outline. And then tomorrow we focus a bit more on sea ice in the Southern Ocean, more generically, starting with some regional aspects, and then looking at the current and future evolution of sea ice in the Southern Ocean and what we understand and know about it. And as I really like starting simple, I thought we'd have a very brief section on the Arctic, just to make you realize why it's great that you're here looking at the Antarctic, because I think the Arctic sea ice is really simple to some degree. So this is how it looks like. This is seasonal cycle in the Arctic. So this is, for example, last year, March 2023, we have the maximum extent at the end of winter, about 13 million square kilometer. And then in summer, we have 24 hours of daylight, so sea ice decreases, and this is what was left September 2023, about 3.5 million square kilometers of sea ice. And this happens every year. Lots of ice in winter, little ice in summer. But what is probably more interesting is the evolution over time. And so if we look at a summer from today and a summer a bit earlier, this is how the Arctic looked like at the end of summer 1979. We had about 6 million square kilometers of sea ice. Last year we had about 3.5 million square kilometers. So if you don't look at the numbers too precisely, it's about half the area. And these ice floes that are left here are only about half as thick as they used to be. So I don't want to do too complicated math, but half the area, half the thickness. In terms of volume, we have about a quarter left, compared to what we had some 30 years ago. If you more think in terms of graphs, this is how the time evolution looks like. In every single month, and I just brought March and September here, we have a very clear downward trend. So if we look at this September sea ice evolution and we try to look into the future, what we basically as a research community have tried to figure out as to when will the Arctic generally look like this. So when will the Arctic summer sea ice be gone? And I think given everything that we know, when we put the IPCC report together, we ended up concluding that the Arctic Ocean will likely become practically sea ice-free during the seasonal sea ice minimum for the first time before 2050 in all scenarios. Which basically is saying we cannot prevent this from happening. This is based on a couple of papers that we've been working on over the last couple of years. And sort of from a general outreach perspective, in some sense, what we try to get across here is that it has become too late to still preserve this landscape. So we will be losing the summer biome in the Arctic Ocean. And this message of we've been telling the public for decades that this will happen, Arctic sea ice, I think, is the first major landscape where we can basically say it's too late now to still preserve it. So we will see ice-free summers in some years. And we can say that with high confidence. And whenever we say something with high confidence in IPCC reports, we need various lines of evidence. And so one line of evidence goes back to a paper that Julian Stroeve and I put together some 7 years ago, where we basically try to conceptualize how this ice loss in the Arctic works. And what we proposed was that the only thing you really need to understand is the ice edge. So if you look at the main fluxes that come in from the atmosphere, to the south, we have a lot of long wave and short wave coming in, so there's too much heat to have ice. In the interior of the Arctic, we have little long wave, little short wave coming in, so we have too little heat to ever have water. And then there's a magic combination of long wave and short wave short wave coming in that says here's the ice edge. And then we put CO2 into the atmosphere, so we increase the amount of long wave that we get. And so what will happen is that this ice edge moves north to a location where the sum of this new long wave radiation and the short wave is exactly the same as it used to be. And so our conceptual picture was basically when you stand on the ice edge in the Arctic, you cannot tell at which latitude you are. The amount of heat you get will always be the same. In the seasonal mean, this will be setting the location where you can both have ice and water. And if you then do a bit of spherical geometry and conceptualized that this change in long wave is proportional to CO2. What this basically ends up giving you is to suggest that there should be a linear relationship between the amount of sea ice we have in the Arctic and the amount of CO2 that we have emitted. And so in order to test that, we did a very simple graph. We just plotted the amount of CO2 that humans have emitted on the x-axis against the amount of sea ice that we have in the Arctic, and we get a pretty good linear relationship. And we see this same linear relationship in every climate model at different slopes, but still every single climate model shows this very, very robust linear relationship between how much ice do we have in the Arctic and how much CO2 have humans emitted. Again, that was a paper that was picked up quite a lot by the media, because if you actually calculate the slope, you come up with a really sort of intuitive relationship. For 1 ton of emissions of CO2 by humans, the area of Arctic sea ice decreases by about 3 square meters. And so I just looked it up. If you fly from Paris to Corsica, you emit per person around 300 kilos of CO2. So flying here melts 1 square meter of sea ice. And I usually use this the other way around when I communicate to companies or something and tell them, well, if you not eject 1 ton of CO2, you basically preserve 3 square meters of sea ice. So you can use this in a really positive way to make people aware how even little changes make a difference. And what we can then do is simply extrapolate this line to 0, and that'll tell us at which CO2 emissions the Arctic is ice-free. And if we do that, and we derive internal variability from observations, this conceptual model says at around 800 plus minus 300 gigatons CO2 emissions beyond 2020, so by now this number will be around whatever, 600 something gigatons plus minus 300, the Arctic will be ice-free. So there's no magic year when the Arctic is ice-free, there's a magic amount of CO2 emissions. And if you then look at CMIP6 models, and this shows how many models have become ice-free at a certain amount of CO2 emissions, basically the range that the good models, which are shown here, so this is about 1/3 of all climate models, those are the ones that match observations best, match this range almost perfectly. And so we can basically use this combination and say there's a robust relationship between CO2 and when the Arctic gets ice-free. There's a similar story you can do with global mean temperature, again, conceptual model and CMIP6 simulations. Here, the conceptual model gives you a much earlier ice-free Arctic at 1.7 degrees global warming plus minus 0.3 degrees, whereas most CMIP6 models get ice-free at warmer global temperatures. And I personally think these models are wrong in that regard. If you look at the observed sensitivity, they really, really underestimate how much sea ice melts per degree of global warming. And so this would be a case where I actually trust the conceptual model more than the CMIP6 models. But no matter what, if you look at these scenarios, if you look at how close we are to losing the ice in the Arctic, these were the lines of evidence we then used for the IPCC report to say it's basically nothing reasonable we can do anymore. It'll happen at some point between 2030 and 2050 that we observe an ice-free Arctic in summer. Now, just in case you don't really care that much about Arctic sea ice, there's another story to be taken away from this, that relates to the way I love doing science, because I really love simple things. I'm kind of simple-minded, and so working with a conceptual model for me is often much more fun than running huge climate models, because I don't really understand what's happening there. And in order to illustrate that point, I want to do a very simple, quick thought experiment with you. I brought a pattern here. And if you look at this pattern and I chart you with making this symmetric around the horizontal line, I think you probably all found the solution. Who found the solution? Great. But there is another solution to this, which is this one. And very few people find that. And the reason for that was outlined in a really nice paper by Adams et al. In Nature 2 years ago, which basically said whenever people try to find a solution to a problem, they look at additive solutions. And they rarely ever look at subtractive solutions. And so we all have the tendency, if something doesn't work, to put stuff into it. And in some sense, you could argue this is the way climate models have been built. If they didn't work, we just put stuff into them. And I've yet to see a single proposal where somebody says, I want to improve this climate model by taking things out. I've never seen that. But that's basically what I try to do in these sort of conceptual model approaches. Because for me, to some degree, the complexity of climate models might actually mean that we don't know what's really important. And so this conceptual model where you just say, if I just use atmospheric fluxes, no ocean, no dynamics, no nothing, I get pretty close to what we observe. To me says, well, in the Arctic, it's really the main driver of Arctic sea ice also simply changes in atmospheric fluxes. Very simple, no ocean needed, and you get pretty close to what the models show. So that's how the Arctic works. I feel we kind of understand what's happening there. And so conceptual models can carry us really far in understanding and protecting Arctic sea ice, and in my view, actually better than large-scale Earth system models. And I would say that's not quite the case in the Arctic yet. In the Arctic, I would argue that at the moment, none of these models is really helping us to understand what's happening because it's so complicated. And what makes it so complicated and why we have such trouble getting Antarctic sea ice good is something that I'll talk about next. And we'll never really touch the Arctic again. So are there any questions on Arctic stuff?
I will touch the Arctic.
Okay, well, there will be sort of so short. Yeah. You mean this one? Basically, it just means it doesn't matter when we emit CO2. So in the low emission scenario, it might be that we reach this point later than in a high emission scenario because we emit less every year. But the only thing that sea ice and the global temperature at large cares about is how much carbon have we emitted. And therefore often, not always, but often to a very good approximation, if you plot variables as a function of CO2 rather than of year or something, all scenarios actually lie on top of each other. Yeah. And that basically is underlying this whole idea of having carbon budgets for 1.5 degree global warming target or something. So it's really about how much CO2 we emit. Yeah. It's probably what I've plotted here is global mean temperature, and they have always been underestimating it throughout all model generations. However, if you don't plot global mean temperature here, but you plot Arctic sea ice loss as a function of Arctic temperature, all climate models are really, really close to what we observe, which basically says the physics of if you have a temperature rise in the Arctic, the sea ice reduces by a certain amount, is something that is very hard to get wrong. All the models actually were very close to the observations. They're not good when it comes to looking at global temperature, and so the main problem is that they warm the Arctic too little for a given amount of global warming. So they underestimate Arctic amplification. And so when people say, oh, climate models are bad at simulating sea ice, my take would be, you don't have to improve the sea ice model, you don't really have to fiddle that much with that kind of stuff. You need to get Arctic amplification right, which is something that sea ice modelers don't like to hear. But I would say if you want to get sea ice better in the Arctic, you don't have to touch your sea ice model, you have to touch your atmosphere and or ocean model. Yeah. Nico?
If you assume that you were able to reverse the CO2 concentration, would it go back
Yeah.
immediately to the previous?
Not immediately, but with a bit of a delay, but you basically follow that trajectory backwards. So there's a bit of a loop, but it is reversible. Yeah. And so Arctic sea ice loss, I'm not sure, we haven't planned to talk about it, but there is no tipping point or something for Arctic sea ice loss. There's no self-amplification. The reason for that is that there is, of course, in summer this amplifying ice albedo feedback loop, but in winter there are processes that we'll talk about in a bit that always mean if you have a summer with really little sea ice, there will be massive ice growth in the next winter, bringing your ice cover back to sort of the long-term climatological mean. And so there is no dominating positive feedback in Arctic sea ice loss, and therefore it's a nice linear thing. And if you stop emitting CO2, you stop losing sea ice. Yep.
So does it only really care in models about the atmospheric temperature? Does the
Yeah.
ocean and the Atlantic, they transport nothing?
So the ocean heat transport certainly matters in the Barents Sea. So if you want to understand CS in the Barents Sea, you need the ocean. But the kind of success of just looking at the atmosphere and getting basically what we observe, to me says you don't need to look at the details of the heat transport. If you look into why climate models lose ice, about half of them lose ice because of increased ocean heat input into the Arctic, and that the other half loses heat by increased atmosphere input. That's a beautiful paper by Clara that I all recommend you reading. But at the end of the day, somehow this heat ends up in the atmosphere and melts the ice from above. Or if it melts the ice from below, somehow you can parameterize that as melting from atmospheric temperature. Yeah. And which is, by the way, why our initial paper was rejected by Nature, because we didn't have the ocean in there. And then Science said, oh, we do take it anyway. So, yeah. No, I wouldn't put it that way. Most of the year-to-year variability is just given by atmospheric fluctuations, how much low-pressure systems you have passing through. And that is primarily because the Arctic Ocean is very well insulated from the world's ocean. You have just very narrow straits, and so it's much easier to bring heat to the central Arctic through the atmosphere than through the ocean. Great. Okay. So keeping things simple is a good thing, I feel. Antarctic, way more complicated. And the reason why it's way more complicated is that the ocean really, really matters. And that's why why it's great to have you here. Because understanding Antarctic sea ice is very much a problem of understanding the ocean and ocean-ice interaction. And that's why we're here. Cool. So Antarctic seasonal cycle is much larger than in the Arctic. So this is, for example, September last year. We have 14.5 million square kilometer. February of this year, which is usually the time of the annual minimum, we have about 1.7 million square kilometers left. So that's within a year. If we look at the long-term evolution, and if we just compare snapshots, it doesn't look too crazy. So this is February 1979. 2.2 million square kilometer, February 2024, 1.7 million square kilometer. Not much happening there. This is summer, same in winter. September 1979, 15.5 million square kilometer. September 23, 14.7 million square kilometer. Again, not much happening. If you just look at snapshots. The picture changes a little bit if you look at time series. So in February, you could argue there's variability. There isn't much ice you can lose, so variability is low. And we do have some record lows here. But if you calculate the amount of internal variability, there's certainly no significant trend in either of these two. But the thing that really excites us scientifically is what happened in winter, where we had this slow, not significant, but still increase in Antarctic sea ice. And then over the past few years, we have came from an all-time high to an all-time low, which in terms of its magnitude is not too different from what we had here, but it just happens super quickly. And I would argue that the jury is still open whether the ice will just recover from this and there's a hiccup in the system, or whether this really is the beginning of a long-term trend. And Martin will talk a little bit about some evidence that this really is different now compared to what it used to be. But given our still somewhat limited understanding, I wouldn't be too bold about this being completely crazy. I think we'll have to wait probably for a couple of years to see how this continues. And you see, for example, here in summer this year, we had actually a bit of a change of direction there. And if we do the same plot as before, we plot Antarctic sea ice in this time in winter as a function of CO2 emissions. There's just no correlation. And so on these kind of time scales, Antarctic sea ice doesn't react to CO2 directly. But there are other things happening. Things might be delayed. The ocean is doing its thing. Great. That's sort of the large-scale picture of what happens in the Antarctic. Now let's zoom in a little bit. Let's try to understand sea ice. And so what I'll do first is to just visualize how an ocean actually freezes, and then afterwards we'll look a little bit into the physics of what actually happens. And what we need to do, among others, is to also look at sea ice as a material. And maybe just to get you curious, this is a plot showing the heat capacity of freshwater ice as a function of temperature. It's around 2 kilojoule per kilogram in Kelvin. So you need 2 kilojoule to warm a kilogram of freshwater ice by Kelvin. And this is the heat capacity of sea ice as a function of salinity. So for example, if you have a salinity of sea ice 8 grams per kilogram, and you try to warm it from -3 to -2, you have to put in 35 kilojoule per kilogram in Kelvin, which makes sea ice probably the material with the highest heat capacity we have on this planet, by far. Which I find fascinating, and we'll talk about why that is. I just leave it there for now. And so sea ice clearly is different from freshwater ice in many respects, but there are also many things that actually work the same for both. Good, but how do we actually get sea ice? So we need to freeze an ocean. What is shown here in the red line is the freezing temperature of water as a function of salinity. What is shown as the blue dashed line here is the temperature at which water has its maximum density. So fresh water, we all know, maximum density at +4, freezing temperature at 0. And then as we move into real seawater over here, the water freezes before it has reached its maximum density, which basically means if you cool your seawater from above, the water will sink down and be replaced by water from far below, and you have some sort of deep mixing until the entire layer is at freezing temperature, and only then, when you extract further heat, you form sea ice. Different to a lake, where once you are below 4 degrees and you cool it further, you form a layer of light, little dense water, and so you just have to cool your surface layer. So if you have a lake at 4 degrees and you have a night of cold temperatures, you freeze it. But for seawater, you really you produce dense water whenever you cool it until you actually have the entire layer at freezing. And the main thing that then matters when it comes to how deep that water gets, and it's just a reminder for most of you, is how important salinity really is in these temperatures for density. So we are dealing with this water down here, and so the lines are the isobars, isopycnals are almost vertical here. So in this cold water, it's really the salinity that matters, which also then makes the salt release that we've just seen crucial for producing dense deep water, etc. Good, and then maybe at some point we have our water at freezing and we extract heat further. And then it really depends on whether we have calm conditions, so no wind, which we never have anyway. Anybody who's been to the Southern Ocean knows that. Or whether we have turbulent conditions, but let's just go through it. So the first thing that happens in the water column is that you freeze Fresnel crystals. These are basically super tiny crystals looking like snowflakes, smaller than millimeter, floating around in the water column. And if there's no wind at all, these crystals float to the surface to form so-called nylus. And there's a differentiation between dark nylus, which is thinner than 5 centimeters, and light nylus, which has a thickness of 5 to 10 centimeters. And you see both here, where here in this case the light nylus is often formed by having 2 sheets of dark nylus getting on top of each other. One thing that is actually helpful to take away from this picture is that when you have light falling on ice, the light is not reflected at its surface, because if it were, the thin and the thick ice would have the same color. But the albedo of ice is actually set by most of the sunlight getting into the ice and then being scattered and then coming out again. And so if you really want to model the albedo of ice, if you want to model its interaction with sunlight, you need to consider that there is scattering within the ice. And so this, at the surface layer, the albedo is actually quite low, which is why really thin ice is really dark. Okay, I think for more practical purposes, now this doesn't matter in the Southern Ocean. It's never not windy. If it is windy, we basically get all these ice crystals, this fresnel ice, rising around, being mixed through the water column, dampening all the small wavelengths, and so the water gets some sort of an oily experience, and this is then called grease ice. And if we add fresnel crystals to this layer, it becomes sort of more and more dampened, and the fresnel crystals start to lump together to then form pancake ice. And the pancakes bump together, so you form these nice little rims, and eventually they freeze together to form columnar ice. And so if you look at the growth history of sea ice, and maybe this one is the most instructive one, this is an ice core under polarized light. This is the surface of the ice, this is further down. This is centimeters here. And what you basically see are these individual crystals. And what you find here, and Martin will talk more about this, is that the part of the ice that was formed under really turbulent conditions, there the crystals really are all over the place, which is why the top layer here is looking random. But then eventually, and that is depending on how these ice crystals grow, along which axis they grow fastest, all these crystals are aligned vertical, and you get these really nice columnar ice growth with nicely vertically oriented crystals. Yeah, and then eventually you get this overall sea ice cover. So that's how sea ice grows. That's just some names so you know what we are talking about. Any questions on this? Yeah. Yeah, yeah, yeah. And we'll talk about more. Yeah. Yep.
What sort of time scale does all this growth happen on? Are there things that can affect how quickly ice grows?
Days. So once you, the thing that really takes time is to cool your water column down to freezing. And once you have that, then you can grow a couple of centimeters of ice in a day. Yeah. Great. So that's the descriptive part. And I just look at the time briefly. We have a couple of minutes left, so I would like to get started on, and maybe I'll just use the whiteboard over here. Maybe getting started a bit on latent heat, sensible heat, because we need to talk about these terms quite a bit, I guess, over the next days. And I often feel that they're a little bit muddled when you ask what do we really mean. And so what I always find helpful is to look at a diagram where we have the enthalpy or energy content maybe on the y-axis. We have our temperature here. And if we start at some plus degrees at a certain, and we define this is a certain amount of enthalpy, and we take energy out of our system, our water gets colder. Yep, very simple. This thing has a certain slope, and this slope is the heat capacity of water. Heat capacity of water describes if I take away a certain amount of energy, how much does my water get colder? And so basically what I'm doing here, and this is the removal of sensible heat, I make my water molecules move slower. So I remove kinetic energy from the system. The molecules move slower, which then means the temperature drops. Until I reach 0 degrees, at which point if I keep removing heat, the temperature stays at 0 degrees. And what happens there, I form fresh water into freshwater ice. And so I don't remove kinetic energy, otherwise the temperature would change, but what I remove is potential energy. The molecules arrange in a different way. And therefore the temperature stays the same, but still the energy is dropping. And then once it's fully frozen, and I keep removing energy, my ice gets colder. Again, we have heat capacity here, and the length of this line, that's the latent heat of freezing. And so this is how sensible latent heat, potential energies, kinetic energy is all connected. And I kind of like this visualization to understand how they all sort of work together in a way. Good. But how do we now grow ice? I'm not sure if you can all see this part of the blackboard. If I plot our ice here. So let's assume we have a certain layer of ice. The ice has a certain temperature at the top. It has a certain temperature at the bottom. And let's assume it's winter, so it's cold at the top and warm at the bottom, which means that we have a heat flux through the ice. The heat flux through the ice is just given as a conductive heat flux, where K is the conductivity of our ice, and dt dz is our temperature gradient, which we can approximate for many problems as a linear temperature gradient. So we can just write T top minus T bottom over our ice thickness H. So this is our ice thickness H. And so all the time we keep removing heat from the bottom of the ice. But what we assume is that for now is that the seawater is at freezing temperature, so we can't make the water any colder. There's no more sensible heat that we can remove. And so what we remove down here is latent heat. And so there's a balance down here, if we look at the heat flux balance down here, that the heat flux into the ice is the same as the latent heat conversion that we have down here to grow ice. And then our final ingredient is how we can actually express this. Well, obviously, the amount of latent heat that we move away down there per unit time has to have the latent heat of freezing somewhere in there, but that is per unit mass. It's easier if we make it per unit volume. So we put our density in here, and then our change in ice thickness. This term up here, L times rho times dH, that describes how much heat we have to remove to form a certain amount of ice. Does that make sense? Cool. And this is per unit time. And then we can say, well, heat flux in the ice is equal to the latent heat flux down there. And if we linearize things, we have an ice thickness here, we have an ice thickness here. It's beautiful differential equations that we can solve. And what we get if we do that is that our ice growth as a function of time I need a minus here, is given by a square root function. So for constant surface temperatures, sea ice grows as a function of time, like a square root curve. And we can understand that as our ice gets thicker by a certain amount, the heat flux becomes less because our gradient becomes weaker, so we remove less heat, so the ice growth slows down. As it gets even thicker, the ice growth slows down further and further. And therefore, ice growth is super, super fast when the ice is thin, and super, super slow when the ice is thick. And this solution here of this stuff, that's called Stefan's law. And what I suggest is that we maybe just leave it here for now. And what we do after the break is to then look what happens now if we add an ocean down here. As a teaser, you oceanographers, you want to know what happens if we add an ocean, if we add ocean heat fluxes. So let's do that after the break. But we do have 1-2 minutes left for questions. Great, welcome back. Did any further questions emerge during the break? Good. So it was good. Then you focus on other things, which is really nice. So you're super refreshed, and we can move on. And so what we'll do next is we'll add an ocean to our system. So let's assume that our ocean provides some heat to the ice bottom. We call that an ocean heat flux. Our system doesn't get crazily complicated then, but then the heat flux balance suddenly becomes that the heat flux that goes into the ice is balanced by, the latent heat flux from ice production and the heat flux that comes from the ocean. So we need to remove the heat that comes from the ocean through the ice, and anything that is left, so if we rearrange that, the latent heat flux, which is proportional to ice growth, is then given as the heat flux through the ice minus the heat flux from the ocean. And if the heat flux from the ocean is the same as the heat flux in the ice, this is 0, and we get an equilibrium ice thickness. And so in any region of the world, we will have some ocean heat flux, and that some ocean heat flux basically determines how thick your ice can possibly get. And so without the ocean heat flux, it just gets thicker and thicker, square root behavior until infinity. But with an ocean heat flux, there's a limit once these are the same. And if the ocean heat flux at some point gets larger than the heat flux in the ice, our ice gets thinner. Good. And in some sense, that's, on that perspective, all we need to know. The problem with the ocean heat flux is that it's a little bit complicated. If you look into the details of what's happening there, maybe just to illustrate that, what's this? Himmelfahrt Hamburg, just in case you wondered. Let me just... and Brückentag frei, just in case. Sorry about that. So in order to illustrate that the ocean actually is a complicated thing, and ice-ocean interaction is actually even more complicated, what I brought here is from a PhD thesis that we did with Thomas Keitzel, a very clever PhD student. And what we tried to understand is how the ice-ocean interface really works. And so what we did, or what Thomas did, he used a direct numerical simulation of basically the ice-ocean interface. And what you see here, these plumes, this is sort of without any background currents or anything. This is just buoyancy-driven turbulence you get undersea ice. Little anecdote, in Hamburg where I work, we have a huge building, the German Climate Computing Center, where we run our Earth system models. Big computers, but those were too small to run this 30 by 30 by 30 centimeter box. So we had to go to an even bigger computer to do these kinds of simulations. But the structures you get, if you do that, are very similar to what you get when you measure things. So if you, and you can also derive some theory as to how quick your ice should melt as a function of temperature, which is this solid line here. The dots here are measurements, are simulations, the crosses are lab experiments. And so it all works out pretty well. And so if you really want to focus on the details, no turbulence, nothing, it works pretty well. But it's complicated. And in order to make you understand what really is complicated about it, when it comes to having an ocean, I would like to do a little thought experiment. We don't have time to do it properly. So I put in some fresh water into this glass. And we also have some salt. And of course, if I add exactly this amount of salt, we will exactly have salinity of Southern Ocean seawater in this glass. And so what happens if I put this glass into a freezer that has a temperature of -1? Anyone? Doesn't freeze. It'll just, there's a glass of salt water in a freezer. And then, magically, we also brought some ice cubes. And they are freshwater ice for simplicity. So it's an iceberg. What happens if I put this ice cube of freshwater ice into my same freezer at -1? It'll stay ice. Yeah. So if I take both these things, put them in a -1 freezer, they will stay like that forever. Okay, that's the boring part. Now, let's assume that I have an iceberg in my salt water. And I put this thing into my -1 freezer. What will happen? And I want you to talk to your neighbor for about a minute or two to tell me what will happen once we put the two together. If we don't put them together, they won't change. If we put them together, maybe they won't change, maybe they will. All right, any ideas? So maybe we I know it's a fascinating thing. We could talk probably about it for hours. I need to stop you here. It's a shame. I would have loved to just keep this going for an hour or so and see what happens. And maybe just take a quick show of hands. So if I put this in a -1 freezer and I open the door after a day, who thinks I will still have liquid water in this glass? Okay. Who thinks I will still have the ice cube floating in there? No, I just talk about whether there will still be water in here. And the second question is whether there will still be an ice cube in here. A couple of days, 1 day, yep. The ice cube is actually, it's a normal ice cube thingy. But if you want, we can wait for infinite times if that makes it easier. So we wait for the end of the universe, and then we open our freezer. Will there still be liquid in the glass, and will there still be an ice cube in the glass? If there's a lid on and blah, blah, blah. So who thinks there's still water? Good. Who thinks there's still an ice cube in here? Yeah. And so basically what we have here is an iceberg floating in a southern ocean. And experience shows this iceberg disappears. Or what we have in here is an ice shelf wall in contact with an ocean. And experience shows the ocean does something to the ice shelf. And experience actually shows that the ice disappears. Now the weird thing is we are in a system that is -1 and we're dealing with freshwater ice. So how is it possible that this ice disappears at -1, freshwater ice? And we know this is crucial for understanding sea level rise, all the stuff that Nico will be talking about, but also for understanding ocean heat fluxes underneath sea ice, because the solid part of sea ice is freshwater ice. We'll talk about that in a bit. How is that possible? Why does the ice cube, if I put this into a freezer at -1, disappear? And in order to understand that, I brought, just wait a second. In order to understand that, I brought a candy. Candies are always good. It's a menthol candy. Somebody wants to have it? Does anybody like menthol, eucalyptus candy? I just throw it and see what happens. So if you put this candy, which consists primarily of sugar, into your mouth, experience shows it will not stay in there forever, but it will disappear. Why? I can tell you the melting point of sugar is higher than your body temperature. I think we can agree on that probably. Why does it disappear? Oh, yeah? It's dissolving, exactly. It's the same if you put sugar into coffee, it's dissolving, it's not melting. And an iceberg in seawater, an ice shelf in seawater, sea ice in seawater, unless your water temperature is above 0, which it rarely is in these latitudes, the ice is not melting, but it is dissolving. Yeah, and the crucial difference is, in order for things to dissolve, they need to be in direct contact with the liquid. So if I were to wrap this ice cube, which is gone by now, by the way, if I were to wrap that waterproof and drop it into my salt water and put everything at -1 into a freezer, it will stay frozen forever. And so what it really needs is this contact with the salt molecules in the water. And so in order to understand what actually happens at the bottom of sea ice, at an ice shelf or whatever, you need to understand that there's also salt transports going on. And so if you look at, for example, the temperature field, we have ice shelf in this, or whatever, something vertical, at -1, and we have seawater at -1. We put that into a freezer. It's a small shelf or a big freezer. How will the temperature field look like if our water has a salinity of 34 ppt, grams per kilogram? The temperature at the interface will be lower because it needs to be at the freezing temperature of our seawater. Whenever you have an interface where the two touch, the interface must be at the freezing point of the seawater. So our temperature here is lower than here, so we get some heat transport in that direction, and that heat is used to make our ice liquid. But it is not a melting process, it's a dissolution process where it is important that we always remove the fresh water from here, because if we wouldn't do that, there would be a layer of fresh water forming here, and then our ice cube would stop disappearing. And so that means in order to understand what really happens at the interface between the ice and the ocean, we need to consider 3 equations. One is that there's conservation of heat at the interface. We've just looked at that. Latent heat flux is given by heat flux in the ice and the ocean heat flux. And the ocean heat flux in itself is a function of how much turbulence you have, and the temperature difference between the far field and our interface temperature. That kind of makes sense? But we also need to conserve salt. And so this is the salinity at the interface and the salinity of the ice times the ice melt, ice ablation velocity, tells you how quickly fresh water is added to the layer. And then this fresh water is being removed because we have a salt flux into the ocean, which is given as the difference in the far field salinity and the salinity at the interface. And finally, we also need to have phase equilibrium at the interface. The temperature at the interface must be the local freezing temperature, which we can approximate as a constant times salinity at the interface. And so we have 3 equations. We have 3 unknowns, temperature at the interface, salinity at the interface, and the change in ice growth or change in ice thickness, and we can solve this. And this is what you need to do if you really want to do it properly. You need to understand that you need to have salt transport to the interface. David? This one here? Yeah. So this one just describes that the interface needs to be at the local freezing temperature, and the local freezing temperature is given by the local salinity. Yeah. Yeah. As linear. Yeah. For that temperature range, that works really well. Yeah. Any further questions? And we could talk for hours as to actually why an interface needs to be at the freezing temperature, but we'll maybe do that later over coffee or beer or something. Good. And you can solve that, and if you want to do it properly, you then get expressions for the time evolution of your interface temperature, salinity, and ice growth, and you will figure out, for example, if you don't have turbulence, the velocity with which your ice is getting thinner in this system really depends on the diffusivity of salt, and that's the rate controlling process. If things are turbulent, the differences get a bit smaller, but it really is the salt transport that sets the velocity of your ice ablation. And so this was the kind of stuff I did for my master thesis, where we looked at freshwater lenses forming underneath sea ice, and we tried to understand how this freshwater lens actually reacts to an ocean heat flux. So I basically derived in the sea ice world this kind of stuff, only to then figure out that Adrian Jenkins, a couple of years earlier, had done exactly the same stuff for an ice shelf world. And so we basically reinvented the wheel during my master thesis, but it was nevertheless good to see that it seems to be right if somebody else has come up with the same solution. There are various ways to simplify this. So what is often done in models is to use either a 2-equation approach, where you just say our phase equilibrium at the interface is just given by the far field salinity. So you assume that the salinity at the interface is basically the same as in the far field. or the very simplest, the one equation approach, where you just set a constant in here. And this is basically what has been done in old climate models. You just assume that the ocean heat flux is just given as the difference between your far field temperature and some constant, minus 1.8 or so. And then you might have your friction velocity in here. Good, and I think that's all I want to say for now about ice-ocean interaction, just to make you aware it's not quite as straightforward, to also make you think about little thought experiments and how a candy can help you understand iceberg-ocean interaction, and to make you really aware of this difference between whether a system is melting or whether it's actually dissolving. And dissolving is much, much slower than melting because the salt transport matters. Good. Any questions on that? Yeah.
Can I come back to the thought experiment?
Sure.
So considering that it's a glass container where we don't have any spreading stuff, if the ice cube melts, wouldn't it just create a fresh layer on top, and this layer could then be freezing in the -1? If we don't have any mixture, no spoon spinning around and stuff, wouldn't they just be creating a layer?
Yeah, and that's what we basically mean, that you would put sort of fresh water into the layer, but you would remove that by diffusion. And so it would be a probably pretty slow process, which is also why this experiment is different if you do it in whiskey or in water, because in whiskey the fresh water would sink to the bottom, and in salt water it stays at the surface. And so there, basically, what you just say makes perfect sense. In whiskey, even if it had the same freezing temperature, which it doesn't, it would be much faster because you basically set in convection by creating this freshwater layer. Yeah, and then some whiskey. Great. Any? Yeah. Yeah. Yeah, it stays. Yeah. And you mean and have the whole same thing at 0 degrees or at -1? Yeah, then it stays like that forever. Yeah, yeah, because it doesn't melt. It is, you need the salt to touch thingy. Yeah. Yeah, and so for me, the main difference between melting and dissolution is this thought experiment. If you were to wrap up your ice cube and you put it into +5, it would get liquid. But if you put it into -1 salt water and it's wrapped up, it never would change. It would just, because it will just see the -1. It wouldn't see that there's salt. And if it just sees the -1, it will stay liquid, frozen forever. But as soon as you remove that, then it sees the salt molecules, and the salt molecules change the freezing temperature at the interface. Temperatures change, you get heat fluxes, and then the whole system starts doing stuff. But salt transports matter. Yeah. Good. What about the interior structure of sea ice? Maybe we do a very, very quick drawing again. Where's my chalk? Here. I do this in the corner here, hoping that you can then see it from over there. This is kind of invisible from over there, isn't it? Yeah. You can see it? Okay. Then I go here. So let's assume we have a bucket with water, 34 grams per kilogram, and it's at -1.8. It'll just be liquid. And now we put the same bucket into a freezer at -3.6 degrees centigrade. What will happen? There will be ice forming in here, but the only thing that gets solid in the system is the water. And so if you draw it in a systematic way, not how it looks like in reality, what we would form is ice with a salinity of 0 gram per kilogram, and we would have liquid water with a salinity of around 68 grams per kilogram, because all the salt has been removed from the freshwater ice, and so the concentration in the remaining liquid is higher. And minus 3.6 is roughly the freezing temperature of a liquid with 68 grams per kilogram in it. And so again, this is in beautiful phase equilibrium and will stay like that forever. And we can carry on with this exercise. We can make it colder and colder and colder. And the colder we make it, the more freshwater ice we get and the higher concentrated the liquid becomes, always until it is in phase equilibrium. And then if we move in the other direction, we make it warmer, some of this ice will be dissolved in our salty water, and the amount of ice we have in here will become lower and lower. And this is what happens in sea ice all the time. So this is how sea ice looks like if you look at it from the bottom. This is 1 centimeter. And so all these ice crystals here are pure freshwater ice. And then in between, you have all these dark regions, and they are liquid salty brine. And you also have some brine channels. We might come back to those later. Basically, what happens is that brine comes out of these channels and is then being replaced by seawater that enters the ice all between these crystals here in between. So you get convection cells. But the main thing for our purposes now is sea ice really is a mixture of freshwater ice crystals and really salty brine. And the salinity of this brine and the amount of freshwater ice is just given by the temperature. So if we know the temperature of our ice, we know precisely how salty the brine is, because there is this one-to-one relationship between temperature and brine salinity. And there's no way you can ever get away from this curve. So if you want to know your brine salinity, you need to know your temperature. Another quick thought experiment. Let's assume that we have more ice. Let's assume we have more ice. Oh, we can just take this one here. Oh, that's sea ice already. Let's take freshwater ice. So this is our frozen road, freshwater ice. And now somebody comes and puts salt on top, like this. Now we have no longer freshwater ice, and it makes weird sounds. What happens to this temperature in this system? Yeah, it will drop, exactly, because now we have put salt on top. So in this time we did it the other way around. We prescribed the salinity, which basically means the temperature needs to adjust. And so whenever people walk around and put salt on the streets in winter, they make the ice colder to get rid of it, which again is a bit counterintuitive, but because of dissolution, this works out. And this is an important experiment, and you will, it might be the only thing you will ever remember from this course, from our CS course, because if you ever give a party and there are lots of people coming and your drinks are not cold yet, you put lots of freshwater ice into your shower tub thing, and you put salt on top, because then the ice will cool down to whatever, minus 10, minus 15, and then you can put your drinks in there and they will cool down much, much quicker as opposed to just putting them into freshwater ice. Yeah, so this is really important for good parties to know that a mixture of freshwater ice and salt is much colder than 0 degrees. The old Romans used that, for example, for keeping stuff cold. And this is important if we want to understand how much liquid we have in sea ice. And in order to understand that, we briefly need to introduce the so-called bulk salinity. So the brine salinity that we've just looked at, that is the salinity of the liquid brine. The bulk salinity, that is the salinity you would get if you take a sample of sea ice and you melt it, and then measure the salinity in the meltwater. And so that salinity is given by the salinity of the brine times how much brine we have, plus the salinity of pure ice times how much pure ice we have. Salinity of pure ice is 0, so this term drops out. And what we find is the amount of brine that we have in ice, so phi is solid fraction and 1 minus phi is the liquid brine fraction, is just given by the salinity of our melted sea ice sample divided by the brine salinity, and that's just given by temperature. And so if we take ice cores in sea ice research, we measure 2 things. We measure temperature along the ice core. We then cut it into slices. We melt the slices. That gives us bulk salinity. And we can then use this expression to derive a profile of how much solid ice is there actually in this core and how much liquid is there in between. And whenever we make our ice, and we've just seen that, whenever we make our ice, for example, a bit warmer, our brine salinity will decrease, and we get more and more brine. And so sea ice does not have a fixed melting temperature. Whenever you make it warmer, it gets more liquid. And it will have disappeared once the brine salinity is the same as the bulk salinity, which can happen whatever at minus 0.6 or minus 0.7, but there's no sort of one-phase transition at a certain temperature. And that is the reason why the heat capacity of sea ice is so high, because if you make it warmer, you heat the brine, you heat the ice, but you also have to make some of your ice liquid. So you also have to shuffle in latent heat for each temperature change of sea ice. As basically expressed by this expression here. We can simplify that in models that we assume often a fixed melting temperature. But if you look at the details, sea ice doesn't have a fixed melting temperature, but just gets more liquid as you make it warmer. Any questions on that? That's a bad sign. It probably means you're all shocked or confused or something. Maybe if we just quickly go, quickly just go back to this one here. So the main thing we need to take away, sea ice is this mixture of freshwater ice, solid brine, and the amount of both is given by how much salt we have in total in our sea ice and the temperature. Good. Which then means that we can very briefly move on to look at how salt actually gets out of sea ice, which is another component of this ice-ocean interaction thing that is interesting to look into. And it is interesting to look into because if we look at deep water formation sites, Ross Sea, Weddell Sea, Labrador Sea, Greenland Sea, at least these two here are in regions where we form a lot of sea ice. And the sea ice, when it forms, expels salt into the underlying ocean. And if we wouldn't have that, our oceans would be much warmer. So this is from some of the paper that dropped out here. It's from a paper by Stössel in 2002. What they did is use a model, and the red line here shows global mean ocean temperature as a function of depth for normal salt release from sea ice. And then in the blue experiment, they just assume there's no longer salt release from sea ice. So sea ice has the same salinity as seawater. And what happened is that the oceans warmed by 3 degrees, which is massive. Which basically shows, or is one way of expressing that we have much, much weaker formation of deep water if we wouldn't have salt release from sea ice. And so therefore, it's important to understand how salt gets out of sea ice. And it's also important to understand the sea ice itself, because as we've just seen, the amount of salt sets the amount of liquid we have in our ice, and that sets all the properties of sea ice. Heat conductivity, mechanical stability, how much algae can live in here, albedo, all these kind of things are set by the amount of liquid. So we really, really need to know how much salt we have in ice. We need to understand how it gets out. Yeah.
What is it about the crystal structure which traps the salt water within it? Doesn't allow the salty water to just
We'll
drain
get to that. We'll just come to that in a moment. And so people have looked at that for a long time. So up to around 2000, there was a list of 5 processes with a general understanding that salt release at the advancing front was the most important process. And a large part of my PhD was looking into how salt gets out of sea ice. And as a result of that, we basically concluded all these processes don't matter. And in the Southern Ocean, a process called gravity drainage is basically the only one we need to know about. And I kind of loved it that something as fundamental as how does salt get out of sea ice was still unclear a couple of, whenever I did my PhD, 2006, 7 or something. And I always feel that like sea ice research is now at a stage where oceanography maybe was 50 years ago and meteorology was 100 years ago. There's still some really, really fundamental questions open that we haven't fixed yet. And so I just want to really quickly look into this salt release at the advancing front thing, just because there's some general stuff to be learned there, and then quickly explain these processes, and then we call it a day for sea ice thermodynamics. Good. Salt release at the advancing front. There have been a couple of papers, for example, going back to 67, 71, 88, which basically all said most of the ice is, most of the salt is pushed out of the ice ahead of the advancing front. And that was derived from a alloy metallurgy theory by Burton, Prim, and Slichter. And the numbers were usually around 30 to 90% of the salt does never really enter the ice, but is being pushed out at the bottom. So that was the general understanding. And generally, my master thesis, my PhD thesis was about using so-called Machileia equations to understand sea ice. Machileia equations is a system of equations that describe conservation of heat, salt, and mass, and how they all interact within sea ice. And if you solve these, what you get is the result that across the ice-ocean interface, all the fields should be continuous. So the solution of these equations says there should be a continuous temperature field, there should be a continuous solid fraction field, so directly at the interface, the ice has 0 solid fraction, and then as you move into the ice, it gets more and more solid. And if you combine these two, it basically shows there should be no jump between the bottom of ice and the ocean in terms of its salinity during ice growth. So that was what the theory said. We then, you can then go out and take an ice core. So this is part of the field work I had from my PhD. Very thin ice, but the ice core shows a salinity in the ice of around 5 grams per kilogram. Seawater was at 35. I think we can all agree there is a jump. So now we have measurements saying there is a jump, a theory saying there's no jump, which is a wonderful moment for any PhD thesis if you spend hours and weeks in trying to solve these things. Because of course then you have to think about Richard Feynman. It doesn't matter how beautiful your theory is, and it doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong. But I kind of couldn't find any mistake in the theory. And so I just said, oh, probably the measurements are wrong. And so what we did, we built or developed a new instrument that allowed me to measure salinity in sea ice in situ rather than taking ice cores. It's what we call the wire harp. So there's a bit of electronics that I had to develop there. And we put that into the ice. And if we do that, we get these rained dots of salinity. And suddenly the jump disappears. Those are the good moments of doing a PhD. And so what basically happens is when you take your ice core, the brine at the bottom drains out, and you don't measure it. And so whenever you do ice core measurements in sea ice, I would recommend to not trust your salinity measurements in the lower 10 centimeters or so. Good. Yeah. Yeah, no, I'm just confused here by the slides. Anyway, and so basically, this showed there is no salt loss directly at the front. And so that made me conclude, yeah, we can ignore this process of there is salt release at the front. There must be something else going on here. Yeah. Oh, in terms of the salinity profile, it varies regionally. But no matter what you do, as long as your ice is growing, there's no jump down here. Yep. And so how does salt then get out of sea ice? And that's actually fairly straightforward. It's the so-called gravity drainage that happens. And so in winter, when our ice is growing, the ice is cold here, it's warm here, which then means, as we have just learned, our brine is super salty here, it's not so salty here. And so this salty stuff here has a higher density than our seawater. And so we have some high density brine on top of lower density seawater. And so this whole thing is unstable, and the salt wants to convect. And that's basically what happens, that we get brine drainage out of the ice through these brine channels, and that's then being replaced by lower salinity seawater as a return flow. And so we have a net loss of salt from sea ice simply because the brine is denser. And yeah, this thing is called gravity drainage. And most of the salinity profiles you ever find in the Antarctic you can explain simply by this one process. The question now, of course, is why doesn't all the salt get out? And in order to understand that, we need to consider, and I think in the interest of time I won't write it up, I'll just say it. We need to consider a Rayleigh number. And the Rayleigh number basically describes how much energy do we have available for convection divided by how much energy do we need for convection. And the energy that we have available for convection is just the potential energy of the brine. It's denser, there's a distance to the ocean, so we have potential energy. But we need some energy to move the brine around because it's viscous and also because the pore space in our ice is really small, so we have to squeeze it through there. And so at some point there's an equilibrium when our ice has become so solid that the pore space is so small that this movement stops. And therefore not all the salt gets out of sea ice, but there is a limit given by the pore space in the ice. And so these here are simulations by a PhD student, Philip Grevenk, a couple of years ago, where you see up here the temperature evolution in a new model of sea ice that there's a couple temperature salinity field. And you see how always the bottom part of sea ice is really, really salty. So this is this lower layer where the potential energy is not big enough to get rid of the salt. But then as our ice gets thicker, the potential energy increases and then the brine drains out until it reaches a limit given by this green color where then the pore space is so small that the brine no longer drains out. But what can happen is, for example, here you had a heat wave coming through, and when the ice gets warmer, the pore space open up, and then you have another event of actually brine drainage, which is very important in the Arctic or probably also in the Antarctic, which we call the so-called spring drainage, where you basically get rid of old brine and you replace it by new seawater, bring in all the nutrients. And so after spring, because of sort of heat waves passing through, you enrich your ice and nutrients, and then biology can start thriving there. But everything here that happens in winter can be explained by this process called gravity drainage. Yeah.
Because it's driven by gravity vapors, when you have sheets of sea ice wrapping on top of each other, which you expect a pulse of brine convection, it's sitting higher than one.
And then what you also see, in particular if you look over here, as your ice survives the summer, it gets really, really fresh. But that's a process that we primarily only have in the Arctic. Because in the Arctic we get in summer surface melting, so we produce some fresh surface meltwater, and then we have surface meltwater sitting on top of our sea ice, forming these melt ponds, and they want to drain downwards, and they basically replace brine from above by kind of fresh surface meltwater. And you can describe that by Darcy's law, which describes the flow through a porous medium. And what you find is that's a really fast process, and therefore we basically never have, or very rarely have, or just for a couple of days have, melt ponds that are above sea level. So most of the melt ponds you will find on sea ice have drained to sea level because then the driving force has disappeared and the whole system gets into equilibrium. And I think the final thing to maybe talk about briefly about this salt release is related to something that is called snow ice that we haven't talked about yet. If you have a lot of snow on your ice, and that happens a lot in the Antarctic, you can actually put your sea ice surface below sea level, and then seawater can come in from the sides or from below. There was a master's student, Felix Mutt, and we kind of never published that, I don't know why. It was beautiful work that he did. So he developed this model how the seawater then goes into the snow just by using Darcy's law with capillary forces. He did experiments with some liquid colored stuff here, taking out the wall, and the liquid was rising up to here, but then because of capillary forces, it basically filled all the snow. And he was then comparing how fast does the front move in the experiment, how fast in the model, and he got perfect agreement with no tuning parameters. And so at the end of this, you will have snow-seawater mixtures in the snow ice. We don't really understand what happens to the salt in that system. So it's certainly something that if you ever feel bored, you can do some experiments, theory, etc. on. So for me, that is the biggest unknown we currently have when it comes to the salt evolution and salt release from Southern Ocean sea ice, is actually what happens to the salt in snow ice. Great, and with that I summarize quickly. So sea ice growth and decay is described by heat flux balance at the top and bottom. Sea ice and ice shelves usually do not melt when the ocean supplies heat, but the ice gets dissolved in the seawater, so we need salt transport. Arctic sea ice is simple because you can get very far with very simple atmospheric heat balance models. Antarctic sea ice is complicated because the ocean matters, and the ocean is difficult, for me at least. And then when it comes to salt, salt release from sea ice is a key driver of deep convection in the Southern Ocean. It happens primarily through gravity drainage, and most salt is lost directly after the initial ice formation. I mean, you've seen that in the picture, in the simulation. It's just the lowest few centimeters where there's salt in it. And so this early idea that we can parameterize it as a fractionation is not too bad an approximation. It just doesn't capture the physics, but it works well as a parameterization. And then there's additional salt loss when the pore space open up, and surface flushing barely happens in the Southern Ocean. And now you basically know how sea ice works thermodynamically, how salt gets out of it, how ice-ocean interaction works. And you should be super proud of yourself by the amount of things you've learned already today. But there's more. So we have a bit of a technical handover. It will take us about a minute, and then Martin will start moving our ice around. Great. So.